When last we talked, we left the atom according to Rutherford's model. And the last we talked, we kind of determined that the atom has these things called electrons, and it has this center core called a nucleus. What we're going to do now is we're going to actually explore what actually is going on within the atom. We've learned about the parts, but now it's time to learn a little bit more about how the parts work and what they actually do. So Rutherford's model, in summary, had a solid central core. That central core contained the protons and the neutrons. And overall, it was very, very dense and very heavy. But what he also mentioned is that the negatively charged particles, the electrons that were discovered by J.J. Thomson, were just kind of scattered around throughout the atom. And in total, they made up this rough volume of the atom, and it was mostly empty space in between. The question, though, that Rutherford failed to explain with his model was, what do the electrons do? Rutherford's model simply did not explain why the electrons were there and what role they had in the maintenance and the function of the atom. One idea that's been proposed is the idea of light as a wave, and the electrons have a big role within that. We look at light as a wave as a scaled measurement, and that measurement is put on what we call the electromagnetic spectrum. This is a collection of all the different versions of light. We'll talk about how the electrons come to play with that as we develop this unit. The major difference between all the forms of light here on this massive scale is right here, and that has to do with their wavelength, or how long the distance between crest and crest, or trough and trough. The shorter the distance between waves, the more energy that wave contains. So the highest energy waves are down on this end, while the lowest energy waves are down on this end. You've heard of all kinds of different types of electromagnetic radiation. Low energy, such as radio waves, radar, your FM radio, all those can travel great distances but don't contain a lot of energy. In fact, radio waves have so little energy that they actually bounce off of Earth's atmosphere. Thus, they're actually able to travel a very long distance. Maybe you've noticed radio towers and their dishes are aimed up at the sky. Well, they're aimed up at the sky so they can get a greater range. Furthermore, a little bit more energy in a shorter wavelength, we have infrared radiation. We see that as heat. The very small section of the the electromagnetic spectrum that we can see is right here, and that's visible light. All the colors that we see are in that tiny little portion of the electromagnetic spectrum. Then we have ultraviolet, we have X-rays, we have gamma rays. There's actually something called cosmic rays out here as well that have even more energy. The other end of the idea, we actually can equate and come up with an idea numerically about what light does and the way that it works and interacts. All light travels at the same speed. C is the speed of light. The speed of light in the vacuum is one of the constants of the universe. That's 3 times 10 to the 8th meters per second. This crazy looking letter here is lambda, and lambda represents wavelength. The other letter next to it is not a V, it's actually another Greek letter called nu, and nu represents frequency. If you know either wavelength or frequency, you can solve for the other one with the constant speed of light. For example, if you knew, for instance, that green light was hitting a wave and it had a wavelength of 4.9 times 10 to the negative 7th power meters, you could then solve for frequency. Simply isolate the variable. Frequency is going to be equal to speed of light divided by wavelength. Plugging in our numbers, we have that frequency is equal to 3 times 10 to the 8th power over 4.9 times 10 to the negative 7th power. Therefore, the frequency of your wave is 6.12 times 10 to the 14th power. And the unit for that would be 1 over seconds, which we refer to as hertz. We will practice more of these problems in class. It's a very simple calculation where only one number needs to be known. The other way that light can be described is as a particle. So we have, in most cases, it's referred to as either the dual nature of light or the duality of light. And a lot of the evidence that we have points to light acting as a wave, while a lot also points to light acting as a particle. So much so that we actually haven't made up our minds yet, and science is still trying to decide which one works better. Einstein believed that we didn't have to have either, we could actually, in fact, have both. So what we have here is just a diagram just giving you an idea that light can be both a particle and a wave. And down at the bottom is an example of how light does act as a particle. The prime example that we can give, and one that we'll do a lab with in class, is that if you actually excite a metal in a flame, that metal will fall back to its ground state, its initial state, and when it does, it has to give back the energy. And when it gives back energy, it gives so in the form of light, and that can be measured as a certain color. The lab that we'll do, you'll actually change the color of some flames by using some of these chemicals. You can actually see them go up and fall back down, giving off light. This just gives you a little bit of background about how energy and light are related to one another. We will talk more about this in class, and this is more of just an introductory lesson. So write down your questions and be prepared to talk about it in class tomorrow.